Michael Tremmel. First results from the Romulus simulation.
Hi everyone, my name is Michael Tremmel, and I'm a graduate student at the University of Washington. And like Andrew said, I'm going to be talking about black hole physics in cosmological simulations. But I'm not going to be talking about the genetically modified galaxies. I'm going to be talking about a new suite of high-resolution simulations called the Romulus simulations. High-resolution, large-scale cosmological simulations with an emphasis on an improved implementation of supermassive black hole physics. And what you're looking at here is a little movie, a snapshot of our 25 megaparsec volume. You're moving through the snapshot at z equals 2, sort of in slabs, so you're getting an idea of the three-dimensional structure. And you'll notice a lot of these galaxies, these larger galaxies, have extended hot gas plumes coming off of them, extended hot gas halos. And these large-scale gaseous structures are caused primarily by the supermassive black hole physics that we have. All right, so the suite of simulations come in a few different flavors. We have a small 8 megaparsec volume that we use generally for testing purposes, and I'll have some results from that. But our main data source is going to come from a 25 megaparsec volume and a 10 to the 14 solar mass cluster zoom-in simulation. So together, these two simulations will give us roughly over 100 Milky Way-sized galaxies and beyond to study how black holes are affecting galaxy evolution across cosmic time. These simulations are run using Changa, the new N-body SPH code, which takes all of the physics implemented in the newest versions of gasoline, but is able to run efficiently on hundreds of thousands of cores. And we run these simulations on the Blue Water supercomputer at the University of Illinois. So just to speak real quick about resolution, right? These simulations are high resolution. We have sub-kiloparsec resolution. And that's important not only because we care about the physics, but also because we want to actually understand how the structures of galaxies evolve with time, the disk and the bulge. And to do that, you really do need sub-kiloparsec resolution. Here's an example of such a galaxy at this resolution. Andrew showed the same image. We also care a lot about free parameters, right? So there's been already lots of talks about simulations, subgrid models, and of course, this also needs subgrid models. And with those subgrid physics come free parameters. We have a novel approach to constraining these free parameters. We run a large sample of zoom-in simulations at a variety of different masses and explore a wide sample of parameter space. We utilize this kriging method, which is a statistical approach, allowing us to efficiently move through parameter space and zoom in on our best sort of set of parameters that are able to fit the z equals 0 relationships at a variety of different galaxy masses. Okay? So we constrain our models to fit z equals 0 relations at masses ranging from dwarf-sized galaxies all the way up to Milky Way size. That being said, everything more massive would be considered a prediction of the model, and more importantly, everything out to higher redshift is a prediction of our model. And just to be clear, right, we're comparing to star formation efficiencies, angular momentum, gas fraction, and black hole masses that are observed in the local universe. Okay, and finally, I want to spend lots of time explaining the supermassive black hole physics, which are the cornerstone of these simulations. So we improve upon sort of the normal ways that people model black holes in simulations like this in a few different ways. The first way is black hole formation. So we tie formation to having black holes form in high-density, pristine gas in the early universe. This allows us to form black holes without making any a priori assumptions about which halos should or should not have black holes and how many black holes exist in a halo. You can see here on this probability distribution function, the formation redshifts, most of our black holes from our 25 megaparsec volume are forming between redshifts 5 and 10, but we're forming them all the way out to redshift 20. Right? So we're really exploring a new realm of black hole growth in these simulations that would be unattainable if you used more common approaches to seeding black holes in simulations like this. The black hole accretion is done using a modified version of Bondi-Hoyle. So we apply the Booth and Shea 2009 density-dependent boost factor to account for limited gas resolution. But more importantly, I want to highlight this angular momentum support prescription that we have. Right? The way we do it doesn't require that we make any assumptions about the specific mechanisms that are causing angular momentum transport below our resolution limit or about the state of an accretion disk. All we do is recalculate the Bondi accretion rate using an effective potential calculated using the angular momentum of gas on scales that we resolve around the black hole. Okay, this allows us to scale the accretion rate the way we'd expect it to scale without, again, making any explicit assumptions that add free parameters or anything like that. I personally really like this method because it allows us to stay agnostic and prevents us, again, from moving into an overly complicated subgrid regime where, like someone's already said, you end up just being a semi-analytic model with resolution problems. Finally, black hole dynamics. So I published a paper earlier this year that showed that when you apply a subgrid model to account for the unresolved dynamical friction in relatively modest resolution simulations, you're able to attain realistic black hole orbits. And by realistic, I mean black holes that stay at the center of galaxies when they should, but are allowed to become perturbed away from center, and when they do, they sink back in a realistic timescale. Right? This compared to more common approaches that use an advection scheme where black holes are pushed and tethered to the center of their galaxies. Okay? You're actually falling down on realistic dynamical friction timescales. And just to illustrate how important this can be, this is an example of a galaxy forming at high redshift at the same resolution as Romulus, and the white points here are black holes. And you can see in this particular chaotic case that the black holes actually never really sink to the center. They're interacting with each other, interacting with the galaxy. You have this guy over here that's nice at the center before it really starts merging with this bigger galaxy. And it's important that we allow black holes to have these variety of orbits because they will affect their accretion history. Okay, so now finally onto some initial results from these simulations. So from the 25 megaparsec volume, I plot here the accreted mass density from luminous black holes as a function of redshift. And we see very nice agreement with a variety of different observations. So overall, these simulations are forming black holes at a realistic pace. Growing black holes, I should say. The same can be said about stars. So plotting the star formation density as a function of redshift, again, very good agreement with observations. We're forming stars and we're growing black holes overall in a realistic way. But now I want to change gears a bit and look at an individual galaxy. So this is a galaxy taken, two galaxies taken from the 8 megaparsec volume. They're both roughly Milky Way size. And we can follow their stellar mass as a function of redshift. And again, we see very good agreement with observational data from candles. So individual galaxies are also growing the way they should. And maybe more importantly, they look the way that they should. So here we have a color-color diagram showing the candles data in black and gray. The darker points are lower redshift, and you see this evolution up and to the left, eventually becoming quenched galaxies, right? Where over here you're dominated by dust attenuation. And we can compare the evolution from our simulated galaxies, our two Milky Way-sized galaxies, and we see very good agreement with this. I used a very simple model for dust attenuation. I can get to that in the questions. Now, if we changed our model a little bit, instead of having black holes, say we only had supernova feedback, tuned so that we get the correct final mass of our galaxies. We see a quantitatively different evolution in these galaxies. They do not quench, and again, don't look very much like the observed population of Milky Way-sized galaxies, Milky Way progenitor galaxies from the CANDLE survey. Doing the same analysis, if we, instead of using our dynamical friction prescription, we used an advection approach, the same approach in the illustrious simulation, where black holes are tethered to the center of their galaxies, we see that black hole accretion is too efficient, causing galaxies to quench very quickly and never really being dominated by dust attenuation, moving straight up in this diagram to become quenched. And so not only do we overall evolve black holes and stellar populations in a realistic way, but individual galaxies in these populations look realistic. Now, moving on to black hole galaxy coevolution, what can we learn from these simulations? And so plotted here is the mass accretion rate as a function of star formation rate. And we see, just like in observations, we see a trend where high star formation rate galaxies have a higher accretion rate than black holes. And to be a little bit more quantitative with this, we do reproduce this idea of an AGN main sequence in star-forming galaxies. Okay, most of our black holes fall around this idea of an AGN main sequence. But because of the nature of these simulations, we can go a bit further, and we can ask, what about different types of black holes? In particular, what about dual AGN? So these systems are rare, but we've discovered a few of them already. And we can see that systems that have two black holes in them, two active black holes, the most active black hole tends to lie above this relationship. They also tend to have relatively high star formation rates. Along the same vein, I can ask, what about off-center AGN? Again, a type of system that we observe today, and the observations of them are growing, we see that we have the opposite effect. We tend to have lower star formation rates, and we tend to lie below this main sequence relationship. Right? So because our simulations in particular don't tether black holes to the center, not only do we get more realistic galaxies, but we can begin to understand where these sort of transient events that we observe in reality actually fits on this idea of black hole galaxy coevolution, and where a galaxy sort of travels along the main sequence or off the main sequence throughout its life. And so by studying these galaxies, the host galaxies, we begin to connect these observations of these rarer types of black holes to a more bigger picture of galaxy black hole coevolution. And so just to summarize, the 25 megaparsec volume and the cluster are currently running. They'll be done by this fall, so in the next couple months. And again, the data set will be very, very large, and will give us a really good chance to study black holes in this context. And so I'll take questions, and I'll leave up this video here, which is of another set of simulations we have planned, a set of zoomed-in, high-resolution simulations, also with black holes, with a H2 physics and a very detailed approach to black hole formation. This in particular is a Milky Way-sized galaxy at redshift 0, run at a resolution that's twice as good spatially as Romulus. All right, thank you, and I'll take your questions.
Hi, I was wondering what your black hole mass function looked like at redshift 6.
I have not calculated that.
Because I think one of the things that allows Illustrious to be very successful on that end is basically by pinning one black hole in the center of one galaxy, it's allowing it to just scale with the relations. And I guess if you're seeding 10 to the 6 supermassive black holes at redshift 20, I'm not sure what formation mechanism is giving you that.
So I do have some. Where is it? So I have, I think I might have a better version of this plot somewhere. Here we go. So this is a small number of galaxies, but here we have the final black hole mass as a function of stellar mass of the galaxies at the end of the small 8 megaparsec simulation. And you see there is some spread, which you'd expect at this low mass end, since we haven't yet probed the very large mass galaxies, but we do fit relatively well onto this relationship. Most of our black holes do fit along the empirical relations at redshift 0.
What redshift is that?
This is a redshift 0.5.
Yeah, but weren't the simulations tuned to give you that at redshift 0.5?
Right, exactly. Yeah, they were.
So, I mean, I'm not surprised. I guess the question is what's going on at redshift 6?
Right, and that's something that we'll look at in the future.
So if you use your dynamical friction correction and you look at how the black holes are orbiting around each other in details, do you have some first observations of black hole actually merging or coming like very close to each other, especially in the context of this black hole scoring mechanism? Is it something that you see happening often? Or?
Right. We do have lots of mergers. So even in the small simulation here, the most massive black holes on here have merged probably like with several other black holes, at least on the order of like 5 or 6 in the simulation. And so yeah, we do allow black hole mergers, and we have a separate prescription for dictating that, similar to what our group's already sort of done with black hole mergers. So they do happen.
Yeah, how often?
That's something that we're also looking at with the 25 megaparsec volume. We'll have more information about the merger history as well. We do expect a more realistic look because a lot of the black holes, again, will be merging very quickly with the normal sort of advection processes used in like the illustrative simulation. So it is something that we plan on looking at.
Because what would be interesting is to really test the same scenario for early type galaxies or massive electricals.
Right.
In the sense that if you have supermassive black holes coming together in this huge cluster environment, if you have those very wide orbits,
yeah. So we'll be looking at that for sure. Yeah.
Last question from Julian.
Yeah, I'm curious about your dynamical friction recipe interacts with the AGN feedback that you put in the sense that do you see that when you have like a massive outflow, your black holes start wandering out, your galaxies tracking this outflow or not?
So are you asking if the black holes wander away from the center after a large output,
That's right.
Yeah, so they don't. So if a black hole begins stable at the center of its galaxy, so the dynamical friction isn't tied to the gas. It's tied to the stars and dark matter particles, and so the force it feels won't be affected by that if that's sort of where you're getting at. And unless there's a big perturbation in its potential, it shouldn't move away from the center.
Okay, let's thank Michael again.